Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. Today we're going to talk about how waves can carry energy and information. And if you're in my class, you can follow along in the textbook in section 7.6 of the text, although much of the information we're going to be talking about how waves carry information is not really covered in this section of the textbook. So what we've learned so far is a mathematical description of plane waves. Plane waves moving in the z direction, as shown in the diagram here, are given by this expression with the wave vector k, dependent on frequency and the material the wave is traveling through. And we know that essentially they are planes orthogonal to the direction of propagation, or if the wave in this case is propagating in the z direction, the xy plane, where the electric field is going to have a constant value everywhere. Now, of course, that value changes with time, and it changes as you move along a wave. And we've seen examples of that previously. We often see plane waves represented as planes like this that overlap, or even as lines in simplistic two-dimensional representations. And in a more general case, we've also learned we can represent the electric field in a plane wave as a vector expression where the spatial phase is given by k dot r, and k in this case is a vector that has a magnitude that's the same k as over here, but it also has a particular direction k hat, which is the direction the wave is moving in. And the direction the wave is moving in, it turns out, is the direction the wave is going to carry energy. So let's look and try to think about any energy the wave can carry, because we've made the claim that waves can in fact carry energy, and that's why they're useful. Well, it kind of makes sense that if a wave carried energy, there'd be a certain amount of energy per unit area. So, example, if I look at the red box I've drawn right here on my plane wave, there might be some energy per unit area. And in fact, if this is the case, the idea of an infinite plane wave kind of doesn't make sense because it would have infinite energy. But regardless, waves do carry energy, and they carry a limited amount of energy that's spread over some limited area. The way we think about this, essentially, is we know this plane wave essentially has both electric field and magnetic field. We talked about that, and there's a relationship between these. And essentially it's this shifting of energy between electric and magnetic due to Maxwell's equations gives rise to the propagation of the wave. It turns out that the direction of energy propagation and the amount of energy propagation is given by a term called the Poynting vector, which is given by this expression right here. It's the cross product of the electric field with the magnetic field. And so if I were to take my right hand and do the cross product, we see the electric field in the drawing is pointing up in that direction. The magnetic field is pointing out in that direction, and so the Poynting vector is going to be in the same direction the wave is propagating. You notice that both S and K are pointing in the same direction. And the Poynting vector gives us the amount of energy. And that's pretty easy to figure out because we know the electric field is given in volts per meter right here. So you have volts per meter. We know the magnetic field is given in amps per meter, and we can write this because we know an amp is an amount of charge per second, or coulombs per second per meter. And so if we just multiply E and H, we see that the Poynting vector is going to be given in volts coulomb per unit area, that's per meter squared per second. And in other words, we get the amount of energy joules per area per time, or the amount of power in watts per unit area. And of course, we know we can do this multiplication simply because E and H are orthogonal to one another, so you just basically multiply them to get the magnitude of the Poynting vector. So essentially what this says is that plane waves carry a given amount of energy per unit area of the plane wave per time. And the amount of energy they carry depends on the strengths of the electric and magnetic fields, which of course are related through the impedance. So there's essentially the realization that the Poynting vector gives both the direction and the magnitude of the amount of energy a wave carries, but that energy is given in terms of unit area per unit time, or in a power per unit area. The language we use to describe this is that we talk about a power, which is energy per unit time, and the intensity is the amount of power per unit area, or energy per unit time per unit area. If you want to calculate the average intensity, essentially how much energy is being delivered by the wave, you have to average the Poynting vector over one cycle of the wave, just like we did when we calculated average power back with transmission lines, because your field's going up and down, but the power essentially is going to be averaged over the many cycles. And so essentially the average value of the Poynting vector is just the integral of the Poynting vector over one cycle, where t here is the period of the wave. And it turns out there there are various ways to represent that. One of the most common ones and one of the most useful ones is 1/2 times the square root of epsilon over mu, or the permittivity over the permeability, times the magnitude of the electric field squared, going in the direction the wave is propagating. You can also do it as 1/2 times the impedance of the medium times the magnitude of the electric field squared, also in the direction that the wave is going. All these are equal representations, and you can play around with epsilons and mu's and convert to different notations as well if you'd like. One important thing to realize is to bring our concept of flux back in, because this energy is going in a particular direction. Remember, we defined our flux as the dot product of some vector with the area of the net that was catching whatever the vector S was carrying in the direction of the normal to the surface. So essentially we think about capturing the energy flowing in this wave in some area given by this square, and so this square essentially is going to have some kind of area. We're going to call it A, and this area has a direction in the vector normal to the surface. We've learned this before. So in this case over here, if you have a plane wave that's carrying energy, and this should be a K right here, pointing in that direction, then this energy is incident on some kind of, let's call it a photocell or a solar cell or some kind of antenna that's going to try to capture that energy. You'll notice that because this thing is not square on to the wave, it's essentially canted at an angle, that you're going to determine the amount of energy that hits this surface right here by taking the dot product between the Poynting vector S with the normal to the surface multiplied by the area of the surface, and that's going to give you the total amount of the intensity on the surface, the power per unit area, or essentially the amount of energy you're going to collect in some given amount of time over that surface. So again, the concept of flux comes in useful here. So if you can remember this idea of flux and the fact that the energy depends on sort of the angle of the thing you capture it with and the area of the thing you capture it with, and a few simple expressions given by here, it's fairly easy to calculate the energy that flows in a wave. That's really not that difficult. The information that's carried in a wave is a completely different matter, and so let's sort of drop our discussion of energy and begin our discussion of the information that's carried by a wave. And in order to understand the information that can be carried in plane waves, we have to get a little physics on you. We have to introduce the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle really isn't that hard to grasp. It's often presented in a way that makes it really challenging, and it's not intuitive at all. But we really need to understand uncertainty in order to understand information that's carried in plane waves. And so essentially the Heisenberg uncertainty principle says there's a natural limit to the accuracy of any measurement. You can only measure things to a particular level of accuracy. And from an engineering perspective, essentially what the Heisenberg uncertainty principle says is there are fundamental limitations on the performance of systems. You have trade-offs. If you want to get one thing really, really accurate, you have to sacrifice in other areas. And so essentially the way to think about the Heisenberg uncertainty principle is an engineering heuristic, or a very powerful engineering rule of thumb that allows you to estimate the limits of systems. It acts as what I would call a crap filter. You can look at something and say that's not going to work without having to calculate everything out. So how does the Heisenberg uncertainty principle work? So what I've got here and here are two of the many statements of the Heisenberg uncertainty principle. There are other ones, but these are the two we're going to be dealing with. And essentially what the first one here says is that the product, if you multiply how accurately you know your wave vector k and your position, that the uncertainty of those is going to be greater than or equal to 1/2. And I know that doesn't say very much, it's confusing, but stick with me. One of the more common ones is that the how accurately you know your frequency, delta omega, multiplied with how accurately you know your time, delta t, also has to be greater than or equal to 1/2. And so let's take a look at this second one, the Heisenberg uncertainty principle stated in terms of frequency and time, to see how that works. So let's say I have a wave, and let's say that wave is infinite in extent. So in the first case, delta t is very, very long. And if I want to know the wavelength of this wave, essentially what I would do to get the most accurate measurement is essentially know at what point in time that point on the wave is, and what point in time that point on the wave is right there. And then I would simply count the number of cycles. I'd know my time at those 2 points very accurately, and I'd get a pretty good estimate of what the frequency of the wave was, because I would know the time it took to go a certain number of cycles. And this is the case where delta t is very long. Well, let's see what happens when we cut down delta t and make delta t smaller. Now I'm measuring the wave at that point and at that point. I have less time, and the uncertainty of my measurement increases a little bit because I'm measuring over a smaller window and I have fewer cycles to measure. And there's always going to be some uncertainty with how accurately I measure things. What if we cut down the window a little bit more? Now I'm measuring at this point, and I'm measuring at this point. So I've got even a smaller window, delta t, in which to determine the number of cycles, but I can still make a pretty damn good estimate of the frequency of the wave with this time window. But as we continue to decrease that time window, so I'm only measuring essentially one cycle of the wave, my measurement of the frequency becomes less and less accurate. I just don't know it as well as I did when I could measure a lot of cycles. And of course, in the limit where you only look at a small slice of that wave, at this point, if this is the only time window I'm looking at to do my measurement, I've got a lot of uncertainty in my frequency. I'm really guessing at it at this point. And this right here is Heisenberg's uncertainty principle. The size of my time measurement window gives me the uncertainty in how well I know my frequency. And of course, if I know my frequency very, very, very accurately, I don't know when the wave has occurred. I don't know when it occurs because there's an uncertainty relating frequency and time. And we're going to use the word conjugate variables. Frequency and time are what we call conjugate variables. The wave vector and the position in space are also conjugate variables. So let's take a look at two cases and explore some of the limits of this. First of all, let's look at the relationship between position and wave vector through the Heisenberg uncertainty principle. And we know in plane waves, we've stated that plane waves are infinite in extent. So we need some kind of source of radiation that's infinite in order to generate these plane waves. In other words, they stretch for immense directions in that direction. Essentially, what we know is that if we say essentially this is the y direction, we know that there's no variation of the wave vector in the y direction because there is no wave vector in the y direction. Everything here is moving in the z direction. But we also know the extent of the wave in the y direction is infinite. And so the limit of an infinite extent in the y direction gives you zero wave vector in the y direction. Let's look at the opposite extreme, where essentially the waves emanate from a point source. In this case, we know we're going to get spherical waves, and they're going to be going out in all directions. In this case, the extent of the wave very near the source is equal to zero because it's coming from a point. This also says that there is no limitation on the direction of y. It's going in, or the wave vector in y. It's going in all different directions. So plane waves and spherical waves are two extremes of the Heisenberg uncertainty principle. Now that explanation might have been a little bit confusing, so let's take a look at another case, the Heisenberg uncertainty principle in terms of frequency and time. Our plane wave has an infinite extent in time. We know it goes out there to the start of time and this way to the end of time. In other words, the extent in time of a plane wave is equal to zero. If the plane wave has infinite extent, the Heisenberg uncertainty principle says plane waves only have one frequency, and in fact, if you look at the solution to the plane wave, the equation for it, it only represents one frequency. The other extent of Heisenberg uncertainty principles is the engineering Dirac delta function, which we know has zero extent in time. Essentially, this limit of this delta function, delta t, approaches zero for a Dirac delta function. It turns out that the Dirac delta function contains all frequencies. So plane waves really are one extreme of possible solutions. Plane waves are infinite in spatial extent and infinite in time. there's no variation of frequency of plane waves whatsoever, and essentially it also means that there's no variation of the wave vector k of plane waves whatsoever. But we can have other solutions that represent other points on the Heisenberg spectrum that are point sources or that are very constrained in time. So why am I getting all physics on you when what we're interested in is carrying information? It turns out that you have to be able to modulate or turn on and off a plane wave, or change its amplitude in some way in order to carry information. For example, if we think about the plane wave that goes on for an infinite extent in time, it's either there or it isn't, and that really isn't more than one bit of information. What I have to do is I have to turn my plane wave on and off. I have to modulate it, limit its extent in time, as shown in the figure over here, if I want it to be able to carry information. And so I have to essentially window it or put some time-dependent function on my plane wave in order to carry information. So what does this mean? What does the Heisenberg uncertainty principle, written here in terms of frequency and time, tell us? Well, this is really interesting, because if I think of the extent of this wave, essentially, as delta t, it's pretty obvious that if I make delta t smaller and smaller, I can carry more and more information. As the length of my bits gets smaller and smaller, the rate of information that I carry can go higher and higher. But notice as delta t goes smaller and smaller, that delta omega, the range of frequencies that have to be contained in the wave, has to increase by the higher by Heisenberg's uncertainty principle. And we know this in electrical engineering because short pulses have to have a lot of bandwidth, and that's the Heisenberg uncertainty principle. So we know that waves and plane waves can carry information, but they're not really strictly plane waves because they're not of an infinite extent in time, and we have to modulate them. Now, this is a very hand-waving explanation, I'm afraid. If you want to do this correctly mathematically, you have to use the Fourier transform between conjugate variables. And remember, omega and t are conjugate variables. So you can convert between frequency and time using the Fourier transform. But this is for another course. You probably call this course networks or something like this, and you've probably covered this before. But all of this starts to tie together because the plane wave solution we study is the case of an infinite extent, and we have to get more complicated and modulate it if we're going